Welcome to our webinar, Breaking Free of Traditional Manufacturing Constraints. We will begin our webinar in approximately 5 minutes. Welcome to our webinar, Breaking Free of Traditional Manufacturing Constraints. We will begin our webinar in approximately 2 minutes. Welcome to our webinar, Breaking Free of Traditional Manufacturing Constraints. We will begin our webinar in approximately 1 minute. Hello, my name is Al Spada, and I'm editor and publisher of Metal Casting Design and Purchasing Magazine and Modern Casting Magazine. I would like to welcome you to our webinar, Breaking Free of Traditional Manufacturing Constraints. 3D printing and additive manufacturing are exciting topics for today's manufacturers. we have 3 expert panelists for our webinar to dive deeper into this topic. Our first panelist, John Bagliotti, has served as the Director of Marketing and Business Development for ExOne since March of 2015. John started his career as an aerospace engineer with the Rotor Systems Division of Sikorsky Aircraft. Our second panelist, Jeffrey Scheffler, currently holds a Senior Program Manager position at ExOne. In this role, he is responsible for implementing the development and improvement of new finite element design methodologies related to additive manufacturing. Our third panelist is Scott Chapman, who is Director of Engineering Programs at Applied Technology Integration and co-responsible for business development. He has been with ATI for 5 years in various roles, including design, engineering, and project management. Before I turn our webinar over to our 3 panelists, I have one housekeeping item for you. If you have a question during the webinar, please click on the question tab in the GoToWebinar control panel on your screen, and then type your question into the box. We will address as many questions as we can at the end of the webinar. So please welcome our 3 panelists this morning as I turn the microphone over to John Bagliotti to start this morning's webinar.
Good morning, and thank you, Al. So let's get started. We've got a series of slides that we'd like to walk through with you to talk about the background of the technology, the software that we used, as well as the case study to demonstrate the ability to optimize a part, not only electronically through software, but then actually realize that through the freedom of 3D printing and produce the truly optimized casting, in this case, a steering knuckle. What we hope to demonstrate to you is the benefits of using additive manufacturing in conjunction with the advancing software. I think what's really interesting about what you're going to hear about today is probably for the first time, the full strength of the software suites that are available have a complement in the manufacturing platform. So there no longer is a compromise of what you can design and what you can create. What also we're able to do is through the combination of the software, we optimize the part, we can validate that design through finite element analysis. We run the solidification to identify the rigging for the casting, and then simultaneously we're able to produce not only the traditional casting for comparison, but the optimized casting at the same time. The benefits of 3D printing allowed us to avoid the hard tooling. We were able to produce what you're going to see is a highly complex casting, and the entire process from design, engineering, validation, and casting was less than 3 weeks. For those less familiar with binder jetting technology, which is what we use to produce the castings, some of the benefits of it include the ability to produce any level of complexity for a part. There is no cost, as we say, for complexity because there is no hard tooling. We can produce various iterations of the same design simultaneously without the need for patterns. We can use traditional foundry materials. In the case of this example, we used traditional silica with a furan binder. Also, the process is very accurate. We get very tight tolerances on the process, and what you realize in your CAD design is materialized in the final mold package and then the casting. Also, as many of you are probably familiar with locking in a design because of the need to develop your tooling, what's very interesting about this is design changes can be made daily, and we can produce the mold packages within a number of days. So there really is no penalty for truly coming up with a design that is intended. And also, I think there's been speculation in the past, or there's been the claim that 3D printing is good for prototyping. I think what you'll find, and certainly we'd be happy to answer these questions, is that this technology is really well suited for the entire life cycle of a part. Very good for prototypes. We now have the ability to do serial production up to certain volumes, as well as the spare industry, which is a really attractive opportunity to use this technology, especially for parts that have been in service for decades, where the patterns no longer exist or the drawings are in the 2D format. So now we're going to run a short video which illustrates the process that we use. Once we have the CAD file designed, we're able to run that through the solidification software to identify the proper rigging for the casting. We can simulate it, and then we incorporate that into the mold package, which is then assembled. You see here electronically and illustrates the part inside the mold package. Once the design is finalized, it gets sent to the printer. In this case, the S-Max is printing the entire mold package layer by layer by using a Furan binder to hold together the silica sand. The parts are removed from the job box, assembled, as you can see here, and then this is where the traditional process takes over. You pour your metal, and then remove the part from the mold package once it's cooled. And so when you see the castings later in this presentation, that is the process that we use to create them. So a little bit about the case study. This is an optimization project where we chose a steering knuckle as a subject part. ExOne, along with ATI, teamed up we put our engineering teams together and the various software packages that we use to not only optimize the design, but to electronically validate it, to come up with the solidification solution for it, put that into the mold package design, print the rigging with the mold package, and then pour the castings, both the traditional casting, as we said before, as well as the optimized casting. I'm now going to turn it over to Scott, and he's going to walk through the optimization process, which leads up to Jeff's validation and ultimately the casting.
Thank you, John. While there are lots of opportunities for design optimization within any particular system or subsystem, we've elected to look at an automotive suspension component. This automotive suspension component is a steering knuckle, and because of its critical nature on the overall dynamics of the vehicle and the amounts of load conditions subjected to this component, we found and thought it would be a very good part to put through this process. We can back up some of this with engineering validity and end up with a physical part that represents geometry that could not yet be manufactured in any other way. So a little bit about the knuckle to kind of set the stage for what this part is subjected to and to try to put a little bit of real world to the engineering language that'll come a little bit later. When your vehicle travels down the road and makes contact with a pothole, a speed bump that you may have not noticed was fast approaching, you can feel these jolts inside of the vehicle as an operator of the car. These are considered vertical loads, which causes the knuckle to want to accelerate up into the fender of the vehicle. Feel this inside of the car. Additionally, the knuckle is subjected to lateral loads when you traverse around a bend on a street. So as the weight of the vehicle shifts, you kind of feel this in your driver's seat a little bit. You move left, you move right in your seat. The same thing is happening with the weight of the vehicle. This weight is shifted and amplified, sometimes by as much as 3 or 5 times the corner weight of the vehicle. Again, all of these loads or all of these instances of impact are transmitted through this knuckle. So you can see that this knuckle, while it is an individual component, is subjected to a wide variety of conditions and loads within a vehicle. One of the things that is critical when looking at an optimization opportunity is to appropriately define some of the goals, some of the things you wish to accomplish from a design engineering standpoint and ultimately a physical component. Things like, I wish to be lighter, I wish to be more, I wish to use the material in a more strategic manner. Perhaps I want to save weight on the knuckle in exchange for adding weight to another component that might be subjected to some durability issues as an example. You can also increase and modify the driving characteristics or the vehicle dynamic characteristics by putting unsprung mass in places that you wish to have it. You can also change and tailor specific engineering or specific aspects of the component, such as inertia, stiffness, and even thermal characteristics if your part is within a thermal environment. Some of the advantages of goals like this is an increase in fuel economy. Everybody is concerned about fuel economy and looking to get the next mile or two out of their vehicle. Weight reduction offers a tremendous return on fuel economy as well as an increase in vehicle performance. From a product development standpoint, having access to all of these things allows an engineering team to evaluate and ultimately verify competing design concepts in a parallel process. So if there are multiple approaches to solving a singular problem, you can do those multiple approaches all at once, subject them all to the same conditions in the same process without having to stack up the time. You can be done in parallel. An additional goal and benefit it brings to the challenge is production intent prototypes. When you can eliminate as many variable changes when going from prototype to pre-production and production, you get an increase in information and an increase in confidence that when I move through the various phases of pre-production and production, I am not affecting this component's performance or the expected outcomes. The other interesting thing is, as John mentioned earlier, this is really one of the first times we're able to fully exploit the power of some of these software technologies by resulting in a manufacturable product. So what that does is it allows us as engineers and those of us in the engineering community to reduce our intuition on how to solve problems. We don't have to always do it like we've always done it. We can let math, we can let Mother Nature, and we can let organic freeform features solve our problem, and it may be in a method that we could not have conceived as humans. And again, all of this is done using traditional materials, traditional foundry methods, so on and so forth. So I will put a little bit of data behind the demands of this application so you guys can see just what types of forces and those impacts of forces are on product engineering. So a few assumptions. Think of a 4,000-pound vehicle. It has 4 tires, so roughly 1,000 pounds per tire, and the tire has got a radius, once fully loaded, of 12.8 inches. That level of information is used to then describe and define the loads that this component will be subjected to within the application or the demands of this application. So a slide or two earlier, I talked about traversing over potholes, taking a corner quickly, and feeling all of the weight shifts and some of the impacts on this component. That driving experience translates into this engineering data. We're looking at a component which is blocky in shape as intended to allow the software to define where material should be placed and how the loads or stresses wish to transmit through the part. Here is just a continued setup of the wanting to put some engineering validity behind how these components are designed. So in this particular load case, we're looking at braking. Every time you apply your brakes in your vehicle, this particular component is trying to counteract that through the tire and slow the vehicle down. You can imagine some of the forces felt even as a driver of the vehicle when you try to decelerate from highway speeds quickly. All of that force, all of that momentum and inertia is transmitted into this knuckle. So now that you have set up the challenge, kind of identified the specifics that this component is going to be subjected to, you can begin to travel down the optimization process. While the process is far more robust and cumbersome than what's detailed here, we have narrowed it down into 4 simple steps. Basically, there's an idea to concept process where we are defining the requirements, making sure we didn't oversee or have an oversight on something that might be subjected to this component, and creating an overall project plan. After that, we begin the engineering process, which is an execution of the optimized design concepts. Again, I talked about some of the advantages of going down multiple design paths in a parallel or simultaneous path. Those designs are reviewed, and then the designs are subjected to what is referred to in our industry as shape optimization or shape refinements. That will be demonstrated a little bit later in today's presentation. After that, the prototype building process begins. The design is then checked and validated through shaker tables or other physical testing that may be necessary to increase the confidence in the engineering team, and then go into your pre-production process looking for product performance feedback, again during testing, and any other feedback that might be coming from downstream processes. Next slide. So what we are going to look at here is going to be a looping video of the topology optimization process. What this is doing is identifying how the loads and stresses want to transmit through the parts, and then in turn, where do I need to apply material to combat the stresses? This has been something that has been done for some length of time in industry, but the challenge becomes you must constrain the CAE and math-driven models by traditional manufacturing constraints. For example, drafts, undercuts, full correction, so on and so forth. You have to constrain the models and constrain the optimization process, which does not produce a product which is unable to be manufactured. I commonly refer to this as metal termites. To give an analogy, what you're seeing here is sort of blocked knuckle, consuming the maximum volume allowed in the application, turning the termites loose on this, and they're chomping away where they are determined they do not need structure to hold itself up. The additive version of this casting, one slide please. The additive version of this casting is constrained by the traditional manufacturing. We are allowed to exploit undercuts, exploit negative draft, and exploit other things from a design standpoint that were not achievable traditionally. After you come up with a raw shape driven by math of what the desired material placement is, you then subject the component to shape optimization or shape refinements. Next slide. What you're looking at here is the additive version, which is not bound by traditional manufacturing, and you are watching a final step in shape optimization and shape refinement. This is actually looking at moving and manipulating surfaces to get that last final percent, 2 or 3 of weight out of the product while still maintaining its structural integrity. After that, the final component, which has been deemed as an appropriate design solution based on the demands of the application, is put through FEA and additional CAE analyses to verify from an analytical standpoint that the resultant geometry is certainly going to survive in the application. What you're looking at here is a direct comparison. On the left of your screen is the traditional knuckle, which would have been manufactured using traditional constraints and traditional methodologies, showing the hot spots and stress risers shown in red. You can see the part on the right, which is the truly optimized component, mimics the stress locations and mimics the stress and magnitude. Some keen eyes might notice some additional greens and yellows in the part on the right versus the part on the left. This is just giving you, as an engineer, confidence in an efficient use of material. If everything was blue and everything had no stress on it, it is a good indicator that the part is way over designed.
Okay, so in this casting simulation of the optimized knuckle, our NovaCast software shows a fill rate of 7 seconds at 710 C at the top of the intermediate tube. Total solidification time is approximately 18 minutes. Next slide. So with digital sand printing, we can design and print features such as hyperbolic sprues, custom risers that can then control the flow of the metal into the mold. And in this exploded view, we show several parts that we did print on RS Max printer. And there are the physical parts shown as section cuts to see the intricacies of the design. The part would actually be a full component. This is just a half view for just for better visualization. This part was then taken to a foundry partner who used a Kurtz low pressure casting machine, and the part was produced in A356 aluminum. So here's the telltale of everything. Traditional cast weight, 4.2 pounds. And if we move on to the next one, as Scott said, the component passed all load conditions, requirements, stayed within the same footprint, while reducing the weight at a staggering 33%. Here's the section view, so you can kind of see a little better on the internal geometries, which you couldn't on the other component unless you had it turned or physically in your hand.
Yeah, Jeff, being able to use some of the core technology to get additional weight out, you can see this here in the long neck of the knuckle. That's a completely hollow structure as defined by the math models and the topology and shape refinement algorithms. This would be unachievable using traditional tooling. And that paired with some of the other advantages of the optimization process resulting in more organic shapes and nature-driven inspiration, if you will, allows us to achieve that 33% weight reduction while maintaining the performance. I think we talked a little bit about some, did we meet the goals? And the answer to that is absolutely. From an engineering standpoint, all objectives were satisfied. Factors of safety were still within the realm of acceptability.
And finally, we produced a knuckle that is the same as the other in traditional, I guess, in the requirements that were specified.
Right. With respect to plans moving forward, one of when we looked at the castings, because this is such a huge leap in result, as you can see from this picture, the resulting casting does have a lot of organic features to it, and some of them are very unique, and they can lead to some assumptions that is it a good part, is the part complete? The answer is yes, and I think what's really important to understand here is what Scott developed through the optimization software, we were able to produce exactly in the casting. There was no compromise, there was no limitations in what he was able to produce and we were able to produce. There's a perfect complement between the software and the hardware to produce a truly optimized part. Now, because of the heavily organic shapes and features of this part, and because it is such an evolutionary jump, the next step is we're going to produce a casting that is smoothing some of these surfaces and features, but that's only for aesthetics. There is no need to do that, and we really wanted to show this part in really optimized form so you could see that we didn't compromise in any way. Now, if you could, as designers, you could go back and simply say, we want to fair in a curve, we want to fair in a surface over this jagged area. But as you can see from the finite element analysis and all of the software packages that we ran on this, there is no engineering need to do that. I guess now we'd just like to give a little bit of background about both of our companies for those who are less familiar with us. So I'd like Scott, if you just spend a couple minutes introducing ATI.
Sure. Applied Technology Integration is a 30-year-old engineering solutions provider, predominantly providing cast product design, cast systems, subsystems, automotive drivetrain, suspension, chassis, and other dirty sides of the vehicle. Our goal is to always create partnerships with the companies we work with and support and help create an offering that allows products to be manufactured at a cost-effective rates. We are located in Maumee, Ohio, just outside of Toledo, and have been in that geographic location for the entire 30 years of our existence.
So a little bit about ExOne. For those of you who are less familiar with us, we are a leading global manufacturer of 3D printing systems. Our systems utilize binder jetting for both sand applications, which is what this case study utilized, as well as for direct material applications, direct metal, ceramics, and so on. Not only do we design and manufacture the systems, but we also, through our service centers, provide the ability for customers to source parts from us, direct parts or sand molds and cores. Those sand molds and cores can be delivered to any number of foundries of your choosing, and in some cases foundries themselves would have this all as a vertical process. The Dream Center, which Jeff is responsible for, is an enabling asset to ExOne, where we can provide engineering, design, analysis, optimization, and various support functions to customers who either don't have the ability to do these services or haven't yet committed to retasking or hiring people to do it. So Jeff is able to work with customers to help them get through the hurdle of maybe taking a 2D drawing, or all they have is a physical part, and getting it all the way into the CAD environment where he can collaborate with Scott and to optimize the parts if that's the intention, or simply to produce iterations of that design much more rapidly than could be achieved before. We also, to help customers if they need it, we can provide the final casting through XCast. Again, this enables customers to realize the benefits of it as sort of an incubation to full incorporation into their traditional foundry process and their supply chain. So with that, as you can see, Jeff and Scott's contact information is here. And Al, I think we'd like to open up for questions.
Thank you to our three panelists for their spectacular webinar. As we mentioned at the beginning of the webinar this morning, for the Q&A section, we're asking you to please click on the question tab in the GoToWebinar control panel, and you enter your question into the chat box there. We are going to attempt to address as many questions as we can during this webinar session. But one more bit of housekeeping before we get on to our questions. This webinar has been recorded and will be available as a recording later this week. You will receive an email detailing to you how to access the recorded version of this webinar. The first question, panelists, is who do we contact to determine if our parts can be optimized with the processes you outlined today?
Well, I think you could contact either Jeff or Scott. I mean, either way, they'll end up collaborating together on it. So I think you could feel free to reach either one of them in any particular order. Sure.
Yeah, I'd have to say it's a case-by-case basis depending on what your end result is that you're looking for.
Great. Question number 2. Is there a range of parts you would consider or not consider for optimization?
Yes, there is a range of parts. Parts which are simple in geometry traditionally are not necessarily the biggest and most advantageous parts for optimization. You really want to look at complex components, components which are subjected to high demands, component combining, maybe looking at bringing two things into one. Those types of components are very good. Again, you can go up a level to a subsystem level and look at what would be considered good subsystems for optimization. Again, these are mechanical structures that might either be bolted, welded, some other aspect together are good candidates.
Yeah, I would say that I think if we don't want people to think that this was only this process was only applicable to the knuckle. We just use that as an example, but I think there are enough designers out there probably on this webinar who can look at this and identify many other parts in their systems like this where you can optimize it. And if you look at the entire vehicle, for example, we could come up with a multitude of parts, and you start to stack up all the weight savings associated with that, and it provides the operator with a lot more flexibility in whether it's fuel economy, distance, payload, and so on. And again, there was no compromise in any way to achieve that benefit.
Getting into the technology a little bit, the sample or the example you showed today was a transportation part. Can the binder jet process be used for higher volume production, or is it relegated just to prototypes?
Actually, it can be used, and it is used for higher volume. Prototypes, what's interesting is when people say prototype, you really have to define it, because if you're talking about a high production vehicle, 100 parts might be prototypes. 100 parts for aerospace could be production. The parts, depending on their size. But we can produce thousands of parts in the systems we have today, depending on their size, annually, which is certainly suitable for typical production in a variety of end markets. We also had introduced our largest platform, ExSerial, last year, which is tailored and is designed for serial production. So not only is that machine significantly larger and faster than our previous largest machine, which was used here in the S-Max, but you can also you can put these machines together in series to dramatically increase your capacity.
You can also look at hybridizing some of the approaches for higher volume manufacturing needs, where you can leverage this for core manufacture and use some other type of technology for the more outside generic shapes. As mentioned by John earlier in the presentation, we are taking a slight step back due to the nature of these organic shapes and going to look at a smooth version where you might be able to generate components at a quicker, faster pace.
We have another question getting into the technology and the materials used within the additive manufacturing process. Have you had success in the use of alternative aggregates such as chromite, zircon, and olivine in your system?
Absolutely. On this particular task, we use silica M4000. We've used ORC chromite, ceramicite, cerabeads, fused silica, InCast 70, 80, Manly, all known AFS products that are out there.
Talking about the optimization of the casting, what geometry optimization software did you use, and are the algorithms in that optimization software black box in nature?
So ATI uses commercially available CAE-driven software and tailors it to our particular development process and our core competencies in understanding additive and how this process works on tool developments. The algorithms within the optimization softwares and shape refinement softwares are black box, and they are owned by the software OEMs. It is about marrying the technology with an understanding of cast product design and cast product manufacture, and being able to leverage all of that knowledge and exploit some of these tools that become available to us that we can now use and result in true organic, globally optimum product.
talking a little more about the 3D printing side. The question is, what is your cube size, max size you can print, but maybe to discuss that even further, max casting size, try to relate to the people the max size that your printer is able to accommodate.
I think that's actually one of the most interesting things about the technology is there is no limit to the size of the casting. If you have enough metal to pour, we can make a casting that big. Because we have examples where we've produced 16-foot long castings, 6 or 7 ton part, and that is significantly larger than the job box of the S-Max, which the mold package was produced on. So what we do is we print a series of job boxes and piece together the mold package. So you take a large mold package and divide it up into sections that would print in the job box and then assemble them afterwards. We have case studies where we had a customer that owns one of our machines produced a 50-inch diameter impeller, a 2,000-pound part, and printed a series of the mold packages and then assembled them later and poured the casting. So there really is no size limit to it. It's just a matter of how many boxes would you print in order to achieve the result.
Right, and it's foundry driven. Their maximum weight is really our constraint.
Right. It's really more limited on the foundry's ability, how much metal that they can pour.
There's a specific question about the binder being used in the system. What is the % nitrogen level in the furan binder?
Sorry, Al, could you repeat that? We got cut off there a little bit.
Oh, I apologize. There's a specific question about the binder being used in the system. What is the % nitrogen level in the furan binder?
Actually, I don't have that information. I can reach out to our chemist and get back to you directly on that. That's all of the information I have. I don't have the specific makeup.
Okay. Then let's go on to our last question. What material properties are driving the optimization? Is it stiffness, yield strength, elongation? Those are the 3 that the question recommended.
So the optimization process can be bound by any of those. Whether you're looking to reduce weight and maintain stiffness or go around it with some level of compliance, it's really up to the engineering team and those who understand the nature of the component and what particular aspects of that component from a mechanical standpoint are going to be most suited for the application and your end result. But in general, any and all of those things can be considered and weighted even during the optimization process. If you wish to weight stiffness above and beyond another aspect of mechanical performance, that can be done as well. That kind of goes back to the parallel process and being able to develop multiple designs simultaneously and have those result in multiple simultaneous mold packages without incurring the cost of all the tooling developments and all the changes associated.
I lied. I have one more question for you to finish out the webinar. If we have legacy parts without drawings or files, how would you begin to optimize our part designs?
Well, first we would start with essentially a reverse engineering technique, whether we are using CT or our laser scanning. Go back and create the component in its current state, and then essentially create the model, and then feedback that information with the OEM and discuss where we have the freedom to basically exploit this technology.
And just to add to that, Jeff, if I can, from the design engineering side of things, once the part is digitized inside of a digital environment, CAD or CAE or something similar, if the end user is unaware of the types of loads or application-specific events this component will be subjected to, We can do what ATI refers to as apples to apples comparison. We will take the original structure that's been digitized and break it analytically and look and identify where some of these stress risers are and where some of the concentrations are and how stress wants to migrate through this part. We can also do that with a fatigue study, looking at how many cycles to failure, and get a good baseline, all done on this reverse engineered part. And then we begin the optimization process. And as long as the optimization process results in geometry that is, at minimum, equal to what was found and discovered during the analytical breaking of parts, we would feel confident that we have achieved a livable and survivable product design.
On behalf of Metal Casting Design and Purchasing Magazine and Modern Casting Magazine, I would like to thank our three panelists today for a spectacular webinar presentation. As I mentioned, the webinar has been recorded and will be made available later this week. As an attendee, you will receive an email that will direct you where this recording is available. Thank you to everyone for all of your time today. We really appreciate it. And thank you again to our panelists for a spectacular presentation.
Thanks, Al.
Thanks, Al.
Thank you.
Welcome to the webinar. You have entered as an organizer and may now speak with other organizers or panelists on the line. When you are ready,